Hello everyone. So let's start this session that is preparation for the midterm exam. There might be some questions that we could not discuss thoroughly. So I give one example. Suppose you have a model. You're supposing that yi, which is some variable, is actually linearly related to some other variable. Okay, this is the population relationship between two variables. So the idea is you cannot obviously collect data about all x, y values. What you're going to do is you're going to collect, you're going to sample from x and y simultaneously. So you got the data set z. So the set z is actually giving you the set of x, y, y, and that is equal to I goes from 1 to 3, let's say. So the first value here is the first value of x that you observe is 1. The first value of y you observe is 4. And the first value of x, or the second value of x that you observe is 2. The second value of y that you are observing is 3. And the third value of x and y pair is 3 and let's say 5. Okay, so this is your data set. Okay, now what you have to do is you want to approximate these parameters here, this parameter beta 0 and beta 1, using the sample data. Obviously, this beta 0, beta 1, they are related to the population relationship. They are defining the population relationship between x and y. Meanwhile, you have only the sample, a small sample of three values of these x, y pairs, right? So we know that the ordinal least squares estimator is going to be a good approximation. It's going to be a good estimator given you have random sample, given x and y, the sample, actually this pair, x and y pair is actually sampled randomly. So we know that beta 1, the estimator for beta 1 had, the estimator for beta 1 actually, we denoted by beta 1 hat, meaning that beta 1 hat is not actually the true value, the population value, but this is a good approximation of what is going on in the population, right? Why it is not exactly equal to the beta 1? The reason is some kind of, we're just dealing with a small sample. Okay, we know that beta 1 hat is actually equal to sum, I goes from 1 to 3, you know, xi, let me use lowercase values, xi minus x bar times yi minus y bar divided by summation, I goes from 1 to 3, xi minus x bar squared, right? This is the estimator, ordinal least squares estimator for beta 1. And we know that once you get beta 1, you can easily find the estimator, OLS estimator for beta 0 hat, beta 0 actually. So beta 0 hat is an ordinal least squares estimator of beta 0. So this is an estimator, an approximation of the true beta 0, and that is given by y bar minus beta 1 hat times x bar. Meanwhile, we know that y bar is actually equal to the average of y's, and x bar is actually the average of x's, right? Now let's put them within a rectangle here, right? Now we are ready to go. We can easily get the beta 1 hat, which is equal to, so you take the first value of x, which is 1, minus, or maybe I had to calculate the average of x's and y's. So here I have to say that, okay, I forgot to do it here. Uh, you know that, x bar is going to be equal to the average. So you have 1 plus 2 plus 3. These are the x values. So remember, in these tuples, the first value stands for the value of x and the second value stands for the value of y. So if you take the first value within each parenthesis, you're going to get 1, 2, 3 divided by 3. That gives you 2. And then if you want to find the y bar, you take the second values for each tuple. So you get 4 plus 3 plus 5 divided by 3, which is 12 over 3, which is 4, right? Now let's put that on the parenthesis, actually within a rectangle. Now we are ready to calculate beta 1 hat, and that is actually nothing but, so the first value of x, which is 1, minus the center, the average of x, which is 2, times the first value of y, which is 4, minus the center is, the average of y is 4, plus the second value of x minus the average of x, times the second value of y, which is 3, minus the average of y, which is 4, plus the third value of x, which is 3, minus the average of x, which is 2, times the third value of y, which is 5 minus 4, right? And then you divide everything by, so the first value of x is 1 minus 2 squared, plus the second value minus average squared, plus the third value, which is 3 minus 2 squared. And if you do that, you're going to receive, here we get minus 1. So negative 1 times 0, that is 0. Here also we get 0. Here we get, positive 1 times positive, positive 1 times positive 1. So this is 1 over. And in the denominator, we get, here you get 1, 0, 1. So as a result, we get 2. So the beta 1 has the estimate of the true beta 1 is actually equal to 0.5. And you can use this relationship here. You can say that if this is the case, then beta 0 hat is actually equal to the average of y, which is 4, minus beta 1 hat, which is 0.5, times the average of x's, which is actually equal to 3. Is actually equal to 2. I'm sorry for that. And as a result, you receive 3 for beta 0 hat. Okay, that is how you have to do that. But fortunately, we have a software which is doing it for us. Suppose you have many values. Instead of 3 values, you have like a million values or 1,000 values. You cannot do it manually, right? So you need this kind of software. Now let's do it implement the same thing in the R. Just a minute. Okay. Yes. So we have y value, which is maybe I should start from x value, which is 1, 2, and 3. And then I have y values, which is 4, 3, and 5. And we can plot it, obviously. Plot y, x. The scatter plot is going to be, just a minute, the plot of these points. And then what you have to do is you define the linear model using the ln function y tilde x. And then if you want, you can add it. You can add the line using this AB line function to the plot. Or maybe I had to use some color. You can color with red, so you get red color. That is actually, the relationship here between points, between x and y variables. Actually, that is given by this population regression function. Yes, this is the population regression function, and the line that you get, that is actually the estimate of that, uh, you know, um, that is actually the estimate of the best fitting line. Okay, best fitting line to the data. Okay, so now let's see whether we got. Let's see the coefficients of our linear model, whether we correctly found the intercept and slope. So it turns out that yes, we have correctly specified. We have correctly computed the beta 1 hat and beta 0 hat. So beta 0 hat is 3 and beta 1 hat is equal to 0.5. That is great. So what else we want to do here? You might have this kind of question in the exam. You are given like pairs of 3 points for x and y, right? Actually, it's not correct to say that. I should say that you are given 3 points on the plane. This is how you should say in mathematical terms. So you are given 3 points in a plane, and what you have to do is you have to get the best fitting line. This is how we do that. What else we learn is we can use summary function to get some other interesting things. So if you say summary linear model is actually the object that we have created using the ln function. You can call it whatever you want, apple, peach, tomato, right? Now let's use summary function and see what is going on here. So the intercept parameter is 3, x is 0.5. Interestingly, we have we have a bunch of other information here. We have standard errors, t-values, probabilities, and here you got like r squared, adjusted r squared, and so on and so forth. So why not to delve into these things? Maybe we should start from this, residual standard error. What is this thing? So let me move here. So here you have plane, right? Here you have y values, here you have x values. The first guy is 1, the second is 2, and the third one is 3 for x. So the first value of x corresponds to the y coordinate is actually equal to 4, right? So we say 1, 2, 3, 1, 2, 3, 4. So this is 4. And then you got, for 2 you got 3. And then for 3 you got 5, somewhere here, right? And the best fitting line was something like this, right? passing from 3. So it should actually pass from 3. So you have 1, 2, 3, and 4, and 5 here. So what else? Well, obviously, this line is not actually representing. It's not describing this relationship perfectly, in the sense that you have some deviations from this red line, and these deviations, vertical deviations, they are called residuals. So this is the first residual. Let's use epsilon 1 hat for that. Epsilon 2 hat, that is the deviation of the second point from the line, and epsilon 3 is actually the deviation of the third point from the line. Okay, and you can easily calculate them once you have y values. You have these y values. Obviously, you can calculate the deviation from each point. We can do it here. We can say that, y minus subtract. So we know that the line is this. The line is actually 3 plus 0.5 times x. So these are the predictions. If you are given these x's, if you are given 1, 2, 3 as your x values, the prediction of the model, linear model, is going to be 3.5, 4, and 4.5 respectively. Okay, this is the points on your line, on the red line. Okay, and then let me see whether I can add them here. Probably I have to add x values here also, and say that add is true. Let me see whether I can do that. Okay, no, should be here. So I should say okay, then just a second. We got this. Somehow forgot. Give me a second to see how we can add here. See, so never mind. I forgot somehow how to add it to the plot. I don't know. Well, we can deal with that. Add points somehow. What was the add points? Add points. No. Add. Okay. Never mind. So we got this. Anyway, these are actually our so you are given some x values 1, 2, 3. So the model that you have developed is actually predicting y to be 3.5 given your x is 1, and then if your x is 2, the model, the line predicts that you are going to have y equal to 4, and so on and so forth, right? Then if you want to find the vertical difference between the point and the line, just take each y value and subtract the predictions of the line for those points. And that is all. This is what you get. So 0.5 is the epsilon 1 hat, and minus 1 is the, you see, the second point is actually lying below the line, therefore the vertical distance is going to be negative, and the third one is going to be positive, right? And then what you're going to do is you're going to sum, you have to square them, so to get rid of the negative signs, and then you're going to sum it, okay? And what you receive is 1.5, okay? So this is basically sum of squared residuals. And to get this guy here, to get this standard error of regression, remember standard error is actually found by finding the square root of sum of squared residuals, right? And divide by the number of points, which is 3 here in this case, minus the number of coefficients that we have estimated. We have estimated 2 coefficients, intercept and the slope coefficient. So 3 minus 2, that is giving you, basically that is giving you 1, right? Let me see. Here we got a bit difference. Yes, I know why, because yeah, it's due to the fact that you have approximation here, approximation going on here, right? And I guess it should be actually it should be like this. I made a small mistake here. So remember that you have to take this sum of square residuals, which is 1.5, divided by the n minus k, and take the square root of the whole term. Remember, square root of the whole term, not part of it. Okay, this is exactly equal to, this is almost equal to what you got here. This, in the lectures we called it standard error of regression, but here this is called, in the R output, this is called residual standard error. Okay, and that is basically showing you how well the burst, this red line fits the cloud of these data points. Okay, never mind. So what else? The next thing is the R squared, multiple R squared. How do we find that? We know that if you take this, maybe I should switch to this guy here. So R squared is found by so-called ESS by TSS. So this is the variation in the model divided by the variation in y value. So maybe I should say which percentage of variation in the dependent variable or in y is explained by the model. This is how you can interpret the R squared. Okay, so this is how much, which percentage of variation in y is explained by the model. And we know that the ESS is actually found by, in this case, you have 3 data points. So I goes from 1 to 3. So you take the y hat I, which is, y hat is actually this line, function of this line. Y hat I, so the points on the line, they're the predictions of your model, yes, is actually equal to beta 0 hat, which is 3 plus 0.5 times xi. Okay, so you give me x's, I give you the predictions of the model, and I know that ESS, explain sum of squares, is actually equal to y bar, y I hat minus y bar squared, and sum over the data points. And in the denominator, I have yi minus y bar squared. And remember that the the average of y hat I is going to be equal to y bar. So the average predictions average is going to be equal to the average of the true y's that you are observing. Okay, that is what we mean. So if you are interested in y hat values, so let me use this blue point. So blue dot is actually the prediction of your model. If your x is, if your x is 1, then the prediction of the model is actually equal to 3 point something. Then the second case, if you have x equal to 2, then prediction of the model is something around 4. And then if you have x equal to 3, then your y is going to be equal to 4 point something. Okay, these are actually these blue dots, they are representing these yi hats, okay, for different values of x. Okay, never mind. Now we can actually calculate it. I'm a little bit lazy to do it by hand right now, manually. Let's do it here. So again, y bar, actually y hat I is what the predictions of the model is, right? So it's actually equal, maybe I should say y hat is actually equal to, I'm taking either 0 hat, which is 3, plus 0.5 times x. These are the predictions of my model for different y values, right? For different x values, right? Let me call them y hat. Now, if you want to find the mean of y hat, that is going to be equal to 4, as we have expected. Now, if you want to find the expected sum of squares, that is going to be equal to sum of y minus sum of y minus mean of, actually y hat minus mean of y hat. Then you have to square these values and actually divide by 3 here. I had a little bit of mistake here, because ESS is actually equal to this guy divided by 3 by the number of data points, but because of the division, these two guys, they are canceling each other out. The 3's, they are falling out of the you know arithmetics, and therefore I didn't write them. But in reality, when you say ESS, that is actually sum of squared deviations from the line, and actually sum of deviations of the points on the line from the average divided by the number of data points. Okay, so here this is the ESS. You are taking the deviation of y hats from the mean, and you are basically summing them, summing these deviations and dividing by 3. Okay, let me see. And then the same goes for TSS. TSS is basically the variance of y. You can define it as the variance of y. This is how you find the variance. This is sum of, you have y values minus mean of y, right? And then you take each value and square them. And obviously in the end you have to sum it and then divide by 3. Okay, this is the total sum of squares. And pay attention to the one fact that TSS is actually greater than ESS. This should be the case all the time. Okay. Now R squared is actually equal to nothing but ESS divided by TSS multiplied by 100%, which is 25% here. Again, the interpretation of R squared is the percentage of variation in y in the dependent variable that is explained by the model, or you can say the variation in the dependent variable that is explained by the variation in the independent variables. Okay, that is how we can do it. And one last thing is, let me see what else we got here. Yeah, here you got t-values, right? T-values are found, they're basically found by dividing the estimates by the standard errors. And we have talked about the standard errors. I'm not going to ask you to calculate the standard errors, but you have to know how to calculate this ESS, DSS, standard error of regression by, in a manual way. And you have to know how to derive beta 0 and beta 1 hats using the formulas. You have to memorize this guy. I mean, they are not that difficult. If you understand the intuition, there is nothing to memorize here. So you basically have to know these formulas: beta 1 hat, beta 0 hat, and you are expected to know this R square formula and standard error of regression formula, which is actually sum of epsilon hats. What is epsilon hat here? Epsilon hat is actually the deviation of black points from the line, right? The vertical deviations of these black points from the line, and divide by, you know, n minus k. Here n is 3 minus the number of parameters that we have estimated is 2, right? We have estimated beta 0 and beta 1, so 3 minus 2, that is defining your degrees of freedom. This is how you have to do it here in this particular case, obviously, but the general formula is actually n minus k minus 1. K stands for the number of slope coefficients you have estimated, and 1 stands for the intercept parameter. This is how they write it in a usual way. And obviously, you have to take the square root of this thing. Okay, so you have to know these formulas: standard error of regression, R square, and beta 0 and beta 1. You are expected to know them by heart. And finally, let me define. Yeah, what you are expected to do is you are expected to know the interpretation of these coefficients. Okay, you got 3 and you got 0.5 for the slope. So what does they stand for? Do they stand for? 0.5 is actually telling you that, you know, um, due to the fact that this is slope, so we got this kind of, so we got yi equals to 3 plus 0.5 xi plus epsilon I. Obviously, if you take the derivative of yi with respect to xi, you're going to receive 0.5. So what does this mean? This is actually the rate of change in y caused by a unit change in x. Actually, this, okay, you can define it in this way: the rate of change in y caused by a unit change in x. So if x changes by 1 unit, the expected change, I should say, the expected change in y, given 1 unit change in x. So what we got here is, if x increases by 1 unit, then y is expected on average to increase by 0.5 units. You see here we got positive coefficient, therefore when x increases, y is also expected to increase. Had we had negative coefficient here, you should have told that if x increases by 1 unit, y decreases by 0.5 units. Okay, in this particular case, we have positive sign here for the slope coefficient, therefore once x increases, the y is actually expected to increase too. Okay, what about this slope? What does this slope stand for? Okay, so this actually the intercept. What does this intercept stand for? For the intercept, we got 3. It is actually the intercept. the interpretation of intercept is the expected value of y if x is equal to 0. This is how you have to interpret the intercept coefficient in the model. Okay, so that is the essential things that you have to know. These are the preliminaries of this course. You have to know these things. They are really important things. And here, obviously, you have to know how you get t-value. T-value is basically obtained by dividing the estimate value by the standard error. And p-value, this is the probability. Okay, maybe I have to say that. Just a minute. Um, so I have to say that this summary function is giving me this kind of nice output. What is this? Actually, this is these two guys, t value and p value. They are actually automatic hypothesis testing, or default test of hypothesis. H null is actually telling you that beta 1 is equal to 0, and alternative is beta 1 is not equal to 0. So you have two-sided hypothesis conducted automatically by the R software when you are using summary function. And the same goes for intercept parameter. So it's actually testing the hypothesis that beta 0, the intercept parameter in population, is equal to 0, and the alternative is that beta 0 is not equal to 0. So this two-sided hypothesis is automatically tested once we are calling the summary function. Okay, that is just a preliminary part of what you are expected to know in the exam. Okay, I'll stop at this point. Have a good luck.